Hello, I'm DevPoodle. Today I'll be showing you how to make a depth-based outline using the compositor. So to begin, we want to create a new scene. So let's just create a basic 3D scene. We'll call it example.scene. Then up here you see the sun environment. Next to them we'll have three little dots. We want to add the sun to the scene and the environment to the scene. These are just the defaults, and we need them in the scene so that we can run our compositor effect. Next, we'll add a mesh instance so that we can actually see what the outline effect will look like. So add a mesh. Let's just have a box mesh for now. You can change it later, of course. Next, we need to create a script for our compositor effect. So let's just create a new script. I'll call it outlineeffect.gd. Let's open that up. So the first thing we need to do is make sure it extends compositor effect. And we also need to give it a class name. So let's just call it outline effect. And finally, we want this to run in the editor, so we'll give it an at tool. So there's some script variables that this effect needs. It needs access to a rendering device. So let's call rendering server.get rendering device. We're also going to need a shader. So that's just going to be, for now, it's going to be an empty RID, as well as a pipeline for that shader, which is also going to be an empty RID. And then finally, we're going to need a storage buffer. So let's just call it parameter storage buffer, which is also going to be an empty RID. All right, next we need to create our initialization function for this. So it's just going to be the default init function. We're going to load in a shader file. We don't have a shader file yet. I'll get to that in a moment. But for now, let's just say that it's called, let's say that it's called outline.glsl, which we actually have to specify the type for this. So there we go. From there, we can create a spurv. Then we set our shader variable to the rendering device dot shader create from spurv, and then this. And then we also set our pipeline to a because we're using a compositor effect, we're going to be using a compute shader. So we're going to do rendering device dot compute pipeline create, and then the shader. All right, we've initialized a lot of the things we need to now. Final thing is the parameter storage buffer. So let's create a default parameter data, which let's say is a packed float32 array with 0, 0, and 0, 0. Oh, sorry, actually, it's 4 zeros. And then we set our parameter storage buffer to rendering device dot storage buffer create with the size of the data, and then the data itself. Oh, sorry, we need to change this to a byte array first, so we do dot to byte array over there. And I believe that's it. So now we have our initialization function done. The next thing we need to do is we have to override the render callback function. This is essentially where all our processing will actually happen and where we do the rendering effect. So one thing you'll notice, if we go to warnings down here, is that this variable by default is called the exact same thing as something in this class, which is kind of annoying. So we immediately want to change that, and we won't even be using this at all, so we'll also put an underscore before it, because we're not going to be using the callback type. So from render data, we want to get scene buffers. So we'll create a new variable called render scene buffers and do render data dot get render scene buffers. And then we'll do a quick check so that if not render scene buffer, then we just want to return because clearly something has gone wrong. It's actually called this render scene buffers, just for clarity. Next, we need to get the size that we're going to be rendering to. So we do render scene buffers dot get internal size. Now, it didn't autocomplete that because we actually need to specify the type of render scene buffers. So this is going to be a render scene buffers RD. Then we're going to do another check for size this time. We're going to do size x equals 0 or size y equals 0. Then clearly something's gone wrong and we do not want to render. Alright, next we're going to specify something called groups. This will essentially determine how many times our shader is going to run. So we'll do size.x minus 1, and then we're going to divide by 8, and then add 1 for safety. And then we're going to do the exact same thing for y. But then for z, we're just going to have 1. And then we want to floor this. Next, we've specified this parameter storage buffer, and now we need to actually create a uniform out of it. So we'll just copy and paste this. The only difference is these first two values are now going to be size.x and size.y. The reason we didn't specify them before is because we didn't have access to those variables yet. From there, we can do rd.bufferUpdate in order to set our parameter storage buffer to this new data. So 0, parameter data.size, and then parameter data. Finally, we can create the uniform. So let's call it parameter uniform. It's going to be an rdUniform.new. We need to set its uniform type to storage buffer. Then we set its binding to 0 because we are binding this to the 0th slot of our shader. And then finally, in order to actually give it the data, we do add ID and then our buffer. Alright, this should be a completely working uniform now. We just need to create bindings, which is going to be an array of RD uniforms. For now, it's just going to have parameter uniform in it, but eventually we're going to add some extra stuff. Then we create our uniform set, which is the thing we're actually going to be passing into the compute shader. So we do uniform set create with our bindings. Oh, and our shader, which is going to be our shader, and then our shader set, which is going to be 0. And we also need to create our compute list, which essentially is going to be the directions for running the compute shader. Quite a few lines of code to actually run the shader. So first, we're going to compute list bind compute pipeline, where we just bind our compute list, or bind our pipeline to our compute list. Then we bind our uniform set, which we created. So again, compute list, and to that we're binding our uniform set. Then finally we're going to dispatch it, and then we end it so that it knows that it's over. Alongside this, we have X groups, Y groups, and Z groups. This is our groups variable from before, so we just do groups.x, groups.y, and groups.z. Oh, also requires a set index, which again, as we specified up here, was 0. Then finally, to make sure we don't get memory leaks, let's free RD the uniform set. Alright, now we have basically all of this running. For the sake of reducing errors, let's specify that this groups is a vector 3i. That gets rid of all our warnings. So next we need to actually create the shader, which we called outline.glsl. So unfortunately, Godot does not allow you to edit GLSL using its default text editor, so we're going to have to enter into another text editor. I'll be using VS Code, but you can use whatever you want. You could even use Notepad if you want. It really doesn't matter too much, but I'll see you there. Alright, now we're in VS Code. So we're going to add a new file that we'll call outline.glsl. I believe that's what I called it. So the first thing we have to do is specify that this is a compute shader, and we also specify the version of GLSL we're using. You can just use 450. even if you're watching this in the future, 450 should work just fine. Next, we're going to specify some things about how this computer is going to be run. So we need to do layout and then local size x equals 8. Then we're going to copy and paste this, put a comma, and then just replace this x with y. And then finally, for local size z, this is just going to be 1. Oh, and then we also have to add an in and a semicolon because this is GLSL. All right, next we're going to specify the parameter uniform that we're passing in. So we set its uniform set equal to 0. We set its binding equal to 0. And then we need to do standard 430 just so that it works correctly. This is going to be read only because we're not going to be passing this back to the CPU. Buffer, and then we'll just call it params. Then we specified 4 floats, but we're going to call them 2 vector 2s instead, which is going to be the exact same size, and it's just changing how it gets interpreted by the shader. So we'll call the first one raster size, because that was the resolution of the window that we got from render scene buffers. And the final one is reserved. We're doing this for computer graphics reasons that aren't too important, but it's just helpful to have things aligned. Then we'll give it the name we'll refer to in the code, which is params, but just with a lowercase p. Finally, we'll create our main function. This is where the shader is actually going to be run. Now, there's one last thing. We're going to switch over to Godot for a second, because there's actually another uniform we want to pass in as well. All right, now we're in Godot. As you can see, the outline GLSL is now here. You just can't edit it. It's read only in Godot. So there's another uniform we want to add. So essentially, we want the color texture for the screen. This is given to us by render scene buffers, and it's going to allow us to do post-processing effects. So let's create another uniform that we'll call color layer uniform. It's actually going to be very similar. Let's just copy and paste this, and then change the name. Instead of a storage buffer, this is going to be an image. The binding is going to be 1. They can't have the same binding. They have to be different. And instead of adding parameter storage buffer, we're going to add render scene buffers dot get color layer and then 0, because we want to get the first color layer, which is just like the default. Then finally, we need to add this to bindings. All right, now we're going to go back to the shader. All right, in the shader, we now need to specify the color uniform, which is very similar to how we specified this, but a little cleaner. Layout, we need to specify the input, which is going to be a RGBA 16F. It's still set 0, but this time its binding is 1. So it's a uniform image 2D, and then we'll call it color image. All right, now we have access to all the things we need to actually make a basic shader. For now, I'm going to make a basic grayscale shader because this will set us up with a lot of the things we need in order to make the outline shader. So first, let's get the size, or let's store the size as an image. So vec2 size equals params.raster size. This is normally just good practice in the shaders to assign parameter variables to a local variable in the shader. Next, we'll get the UV. Now, the UV is going to be an integer vec2 that's going to be specified by GL global invocation ID .xy. In this case, we're looping over all the pixels, so this essentially just gives us which pixel we're on, or it gives like a unique ID to each pixel, which is what we're assigning to UV. So next we want a normalized version of this UV, which is just going to be the UV over the raster size. We're going to check if it's outside the screen, and if it is, we just want to return, because that, of course, is not intended behavior. All right, now we can actually do some basic post-processing. So let's get the color from our color texture by calling image load and then the name of the image, so color image, and then finally our UV. Let's get effectively the brightness at each point, which is going to be all of the components of color added up and then divided by 3. And then finally, to actually render this, we do image store, and then we store onto the color image at UV, and then we need to create a vec4 where the first 3 components are brightness, and then the last one is going to be 1 because we want this to be fully opaque. All right, now let's return to Godot and see how this works. All right, nice. As you can see, if you double click on this, you get shader file down here. And as you can see, there's no current errors. So let's go to 3D. And now we want to click on world environment. We want to create a new compositor. And then in that, we add a new element, which is going to be our outline effect. And as you can see, it's worked first try, which I'm a little bit surprised by. Yep, this is a perfectly working grayscale shader. If this is something you need eventually, then maybe you want to save what the shader currently is, but we will be changing this to an outline shader next. All right, in order to get that outline effect that we want, we are going to need access to the depth shader, or to the depth texture. So to begin, we want to add in a sampler for a depth texture, so it's called step sampler. It's also going to be an empty RAD. Then down in this initialization function, we need to create it. To begin, let's create a depth sampler state. This effectively gives us a way to specify settings about the sampler. So we'll say rd sampler state.new. We don't actually want anything right now. Eventually you might want to, change some of these settings, but for now we don't really care about that. So let's just do depth sampler equals rd dot create sampler, or sorry, sampler create? Yes, sampler create with this new blank sampler state. All right, this is necessary so that we can sample from the depth texture because we are going to handle it slightly differently than how we handled the image. So now down here, we're going to basically just copy and paste this again, but call it depth layer uniform. Let's rename all of this. Let's add it to bindings. All right, now there's some stuff we're going to have to change about this. This is not going to be a uniform type image. It's going to be a uniform type sampler with texture. And then its binding is going to be 2. Then we want to add our sampler, so depth sampler. And then instead of getting color layer, we want to get depth layer, which is going to be basically the exact same thing, but just a depth texture instead. All right, now on this end, we should be good. So let's go back to our shader. All right, now here, we need to specify our depth texture. So let's just copy and paste this. We don't actually need to have this part for our depth texture. This is going to be a sampler because we imported it as a sampler with a texture rather than an image. And then we need to just rename this to, I'm going to call it depth texture so that it's clear that, an image is different from a texture, because that's an important thing to be clear with when you're writing shaders. All right, now to make sure we're actually getting the depth texture correctly, we're going to change this up slightly. So let's, instead of brightness, let's call it depth. And let's do texture, depth texture, and then the UV normalized. So I actually need to specify that I'm just getting one of the values because this is actually returning a vec4, I believe, but we just want one of them because depth is just one value. All right, now one final thing I forgot to do is change the binding here. It's really easy to get mixed up with these bindings of different uniforms, so if you're having errors, it's one of the first places I've looked to make sure you're actually assigning them to the right spots. All right, now if we head back to Godot, add in our outline effect, and as you can see, it works. The farther something is, the darker it is, and the closer it is, the lighter it is. Now what we do is we compare the depth of nearby pixels, and if there's a great difference between them, then we draw an outline. Now, this depth texture is not linear. We have to convert it to linear in order to be able to compare nearby depth values properly. So to do that, we'll have to go back into the script, and we're going to have to change up parameter uniform a little bit. So when we initially create it, we're going to do a slightly more dynamic way. Call this maybe just data. It's just going to be a basic packed float32 array that we are then going to resize. So we actually want this to be the size of 20. This is why I'm not writing out 20 zeros manually, is because that would take up a lot of space, and then we fill it with zeros. So as you can see, this is just a much more compact way than writing 20 zeros. And then finally, we replace this whole thing with just data to .byte array. All right, so that's this part done. Next, we need to change how we're getting parameter data down here. So let's do a similar thing. We'll call it parameter data. or sorry, let's just call it parameters. It's going to be this thing, but without the .2 byte array at the end. And now there's something else we want to add to this. In order to get linear depth, we need the inverse projection matrix, which, if you don't know what that is, don't worry, I'll show you how to get it. Let's call it improj map, just for being concise. So we'll get it from render data, get render scene data, get cam projection, and then inverse. This should give us what we want. Then we need to get it as a array. So we'll do same thing. It's going to be a vector4 array, and then this dot x, and then we'll just copy and paste it because it'll make it quicker. So we need to change it to y, z, and w. And then we also need to put brackets around this so that it's properly an array. All right, next what we do is we replace this part with parameters. And then what we're going to do is we're going to append to this, append array. And then we're going to get the matrix array and then do .2 byte array. So now this should actually work, as you can see. So now we have the inverse projection matrix being passed to our shader. So let's go back to the shader. Now we want to add to parameters map4, which is what we just passed in, and we'll call it the inverse projection matrix. So inverse map. So now we will create a function to make depth linear. We're creating a function because we're going to be using this in a couple places, and so it's just going to be easier as a function. So get linear depth, and then we're just going to pass in a UV. So first we get the linear depth, which we'll just call linear, from the texture, just like we did down here, actually. Let's just copy and paste this. But then instead of UV normalized, it's going to be UV. Then we're going to do some math stuff. Don't worry if you don't understand it. You don't really need to. You just need to know that it makes the depth linear. I believe this sort of, or a function very similar to this is in the official Godot docs, but it's for the Godot shading language, so that's why it's slightly different. Alright, as you can see, this is a lot of math. If I've typed everything up correctly, this should all work. But again, you don't really have to worry about understanding the specifics. So the next thing we want to do is, instead of using this, let's do get linear depth, and then we want the normalized UV, and then for, again, just computer graphics reasons that you don't really know specifics of, we're going to add a slight offset that's just going, like an incredibly small offset, like maybe something like this, right? It doesn't need to be big, we just need to add a very slight offset so that everything works how you would expect it to. So we don't really want to render this straight to the color image. What we're going to do is we're going to create a float called depth border, and then instead of doing this vec3 depth, we're going to put in the color.rgb. So this is just the default screen color that was rendering before, and then we're going to multiply by depth border. Assuming everything's gone correctly, this should be the exact same. I mean, actually, once we specify it to 1, now everything should be the exact same as if there was no effect at all. So now we need to do some comparison. And basically, we're going to see if two depths are far enough away, and if they are, we're going to set depth border to 0, which means it will render as black, which means there will be a black border around everything. So we're also going to specify a sample size, which is going to be a float. This essentially specifies how big our borders are going to be. So let's just start out with 5, maybe. That should work. Now we're going to do a for loop, or a multiple nested for loop. So we do float x equals negative sample size. We want it when x is less than or equal to positive sample size, and then x plus plus. This is just how you do for loops in C-like languages. And then I think we're going to tap that. Okay, now we can do some of the actual processing. The first thing we're going to do is immediately call some instances. So in order to make our border slightly rounded. Otherwise, it would have like jagged edges. We're going to do vec2 xy, and we're going to get the length of that. And if it's greater than sample size, we just want to return, or sorry, we just want to continue. Essentially, what this will do is it will just round out our borders a little bit. So then we need to get the depth value we're comparing it to. We'll call that offset depth because we're going to be offsetting it by some amount of pixels, and it's going to be get linear depth. And then we want the normalized UV plus the X and Y variables, and then we normalize those as well, and then we finally add in that little offset at the end. Then what we do is we see the distance between these variables, which is going to be the absolute value of the depth minus the offset depth. And if this is greater than, let's say, 1, then we want to make depth border equal to 0, and then break. And then finally here, if depth border is 0, then we want to break. This effectively is just like a slight optimization. So if we set it to 0 here, we just want to skip everything else because it's already 0. Alright, apparently there's a mistake I made. Oh, these are commas when they're meant to be semicolons. Alright, I actually made another error. I forgot to replace these with Y, so yep, I really should have checked that beforehand. I'm sure some of you probably already noticed. Let's also do slash equals there instead of just a slash. Again, I'm sure some of you noticed that. Sorry about that. Now finally, if you head back, this should just work now, hopefully. And it works. If it didn't work, you may need to restart Godot or recheck your shader code. As you can see, this is a pretty decent outline effect that works dynamically, so we can duplicate the objects. Let's move it around here. Hopefully you can tell that the size of the outline is something far away and the size of the outline something close to us are the same. So this is a pretty decent looking outline. Let's try some more shapes, like a torus, for example. It works pretty well. Thank you for watching. Goodbye!